Welcome. In this video, we'll explore how agentic systems powered by large language models, or LLMs, are reshaping a wide range of industries. Building on our previous discussion of risks and challenges, we now turn to the practical side, real-world use cases and applications. Agentic systems combine the advanced reasoning of LLMs with goal-directed behavior and autonomous decision-making. This enables them to understand context, plan, and act to achieve specific objectives, all while maintaining meaningful interactions with humans. As we move through this video, you'll see how these systems are not just language processors, but core reasoning engines that adapt, learn, and operate with increasing autonomy, always aligned with human intentions. Agentic systems are making waves in four main domains: creative and artistic applications, natural language processing and conversational agents, robotics and autonomous systems, and decision support and optimization. Each of these areas demonstrates how LLM-based agents are moving beyond traditional AI, adapting their behavior, learning from interactions, and operating with greater autonomy. In this video, we'll walk through each domain, highlighting real-world examples and the unique capabilities these systems bring to the table. By the end, you'll have a clear understanding of how agentic systems are transforming automation and human-AI collaboration. Let's start with the creative world. LLM-based agents are revolutionizing creative workflows by understanding context, maintaining creative direction, and actively collaborating with human artists. Unlike traditional generative AI tools that simply produce content, these agents engage in sustained creative dialogues, adapt to changing requirements, and balance multiple artistic and technical constraints. They're not just tools. They're creative partners, helping artists maintain style, intent, and coherence across projects. Whether it's visual art, music, or writing, agentic systems are enabling new forms of collaboration and creative expression. The evolution of creative agents marks a paradigm shift in how AI contributes to the arts. Early generative tools were limited to static outputs based on prompts, offering little interaction or adaptability. Today's agentic systems, however, actively participate in dynamic, iterative, creative processes. They retain context, learn adaptively, and integrate multiple modalities, like text, images, and audio. This means they can refine outputs based on feedback, understand artistic intent, and align with a human collaborator's vision. The result is a move from static generation to interactive, context-aware, and adaptive systems that truly enhance human creativity. One of the most exciting impacts is in artistic collaboration. Agents can assist artists by maintaining a consistent style and thematic coherence across multiple iterations. This enables seamless integration of human creativity with AI-generated enhancements. For example, an agent can help a painter maintain a specific color palette, or a writer keep character voices consistent throughout a novel. The agent's ability to understand and adapt to creative intent makes it a valuable partner in the artistic process, rather than just a tool for generating content. In music, agentic systems are designed to understand and apply musical theory, adapt to different genres, and collaborate in real time with performers or composers. These agents can suggest harmonies, generate melodies, and even orchestrate complex arrangements, all while preserving the composer's creative intent. The result is a more dynamic and interactive music creation process, where AI and humans work together to produce innovative and harmonious compositions. Agentic systems are also transforming writing and narrative development. These agents can co-create with authors by maintaining character consistency, plot coherence, and narrative flow. They offer creative suggestions while preserving the author's unique voice and storytelling style. This makes them invaluable for writers looking to develop complex stories or maintain continuity across long-form works. The agent's ability to adapt to feedback and refine its outputs ensures that the final product aligns with the author's vision. Let's look at real-world examples. Adobe's Firefly agent system demonstrates how multiple specialized agents can maintain creative consistency across complex projects. One agent maintains brand identity, another ensures asset representation, and a third handles technical specifications. This collaborative system adapts to user feedback in real time, representing a significant evolution from simple generative tools. Similarly, Universal Music Group's AI-powered system uses melody, harmony, and orchestration agents to maintain creative coherence in music production, all while preserving the composer's intent. A detailed use case from the film industry shows how Agentic Systems can bridge the gap between creative vision and technical execution. Film directors and storyboard artists often spend significant time aligning creative ideas with technical feasibility. A multi-agent system can translate the director's vision into technically feasible pre-visualization sequences, maintaining both artistic coherence and production constraints. This approach streamlines communication and ensures that creative goals are met without sacrificing technical requirements. In this multi-agent system, the director agent processes natural language descriptions of scenes and maintains the overall creative vision. The technical supervisor agent evaluates feasibility, considers budget and resources, and proposes alternatives when needed. The visualization agent generates storyboards and 3D previews, adapting outputs based on feedback. These agents work together through shared context, continuous feedback, and real-time adaptation to changes in creative direction or technical constraints. The multi-agent system operates within a complex production environment. It connects to an asset management database for 3D models, a production management system for budgets and schedules, a rendering farm API for visualization, and more. This integration ensures that all creative and technical requirements are tracked and managed efficiently, reducing the need for human intermediaries and enabling real-time collaboration across departments. Traditional pre-visualization tools operate in isolation and require human intermediaries to translate between creative and technical requirements. The Agentic System approach offers several advantages: continuous alignment between vision and feasibility, reduced iteration cycles, creative consistency, and more efficient resource utilization. This leads to faster, more cohesive, and higher quality creative outputs. Agentic systems go beyond simple content generation. They actively contribute to creative decision-making, address multiple constraints, and adapt to evolving artistic visions. Their ability to retain context, understand intent, and balance priorities makes them indispensable creative partners. This approach is now being applied in other domains, such as language processing and robotics, which we'll explore next. Shifting focus, let's look at natural language processing and conversational agents. LLM-based agents excel at understanding nuanced language, maintaining context in complex dialogues, and executing tasks through conversation. They're essential for meaningful human-AI interactions, going far beyond traditional chatbots or virtual assistants. Today's conversational agents represent a leap beyond simple Q&A systems. They maintain complex dialogues, understand nuanced contexts, and execute sophisticated tasks. For example, Anthropic's Claude and OpenAI's ChatGPT can engage in detailed technical discussions, adapting their responses based on user expertise and previous interactions. This makes them powerful tools for both customer service and technical support. Modern language agents have several distinguishing capabilities: context retention, task execution, adaptive interaction, and multimodal understanding. They can remember prior exchanges, translate instructions into actions, adjust their communication style, and process combinations of text, images, and code. This enables them to handle complex queries and provide richer, more personalized responses. Salesforce's Agentforce and GitHub's Copilot chat are prime examples of language agents in action. Agentforce helps customer service reps by maintaining context across interactions and accessing relevant data in real time. Copilot chat supports developers by maintaining technical discussions and executing development tasks. These systems demonstrate the versatility and practical value of agentic language systems. Large organizations often struggle with fragmented knowledge across departments. Traditional search systems can't capture context or connections between information. A multi-agent system can understand, organize, and retrieve knowledge while maintaining context and handling complex multi-domain queries. This approach makes institutional knowledge more accessible and actionable. In this system, the query understanding agent processes natural language questions and identifies context. The knowledge navigation agent maps relationships between sources and maintains context across documents. The response synthesis agent combines information and adapts responses to user roles. Together, they enable dynamic, context-aware information retrieval that's far more effective than traditional keyword-based systems. The knowledge management system interfaces with a wide range of internal and external systems. Document management, communication platforms, project management tools, code repositories, HR systems, and more. It also connects to external APIs for industry news, research, compliance, and translation. An access control layer ensures security and compliance, making the system robust and enterprise-ready. Traditional knowledge management relies on exact keyword matches and static categories. Agentic systems offer natural language understanding, context-aware retrieval, dynamic connection of related information, and personalized responses based on user roles. This makes them far more effective at unlocking the value of organizational knowledge. Having seen the power of agentic systems in language and knowledge management, let's move to their applications in robotics and autonomous systems. Here, the ability to combine language understanding with physical control opens up new possibilities for human-robot interaction and automation. Traditional robots rely on pre-programmed behaviors and rigid control systems. Agentic systems, by contrast, enable robots to understand natural language instructions, reason about their environment, and adapt their behavior dynamically. This marks a fundamental shift in how robots interact with both humans and their surroundings. The integration of LLMs with robotics bridges the gap between human intent and physical action. Modern robotic agents can understand context, learn from experience, and make autonomous decisions, all while staying aligned with human objectives. Key capabilities include natural language understanding, contextual reasoning, real-time adaptation, learning from demonstration, and multimodal integration. Boston Dynamics Atlas Robot, UC Berkeley's Adaptive Systems, and MIT's RoboBrain all showcase how agentic systems enable robots to translate language-based instructions into complex physical movements. These systems can adapt to cluttered environments, solve manipulation tasks creatively, and draw on vast knowledge bases to inform their actions. Traditional manufacturing cells struggle with product variation and unexpected disruptions, requiring extensive reprogramming and human intervention. A multi-agent system can orchestrate a flexible manufacturing cell, adapting to product variations, handling disruptions, and optimizing processes while maintaining quality and safety standards. The system includes a planning and coordination agent that understands production requirements and adapts manufacturing sequences. A robot control agent translates instructions into motion, manages sensor feedback, and ensures safe human-robot interaction. A quality and optimization agent monitors production quality and suggests improvements, while an exception handling agent detects anomalies and manages disruptions. These agents collaborate through shared context, real-time data integration, and continuous feedback. The manufacturing system interfaces with robotic arms, vision systems, PLCS, material handling, MES, ERP, QMS, digital twins, and maintenance management. It also connects to supply chain management, customer order systems, compliance databases, and historical knowledge bases. This integration enables seamless coordination and optimization across the entire production process. Traditional robotic manufacturing systems are rigid and require human intervention for adaptation. Agentic systems enable natural language interaction, real-time adaptation to product changes, autonomous handling of disruptions, continuous optimization, and proactive quality control. This leads to greater flexibility, efficiency, and resilience in manufacturing. This approach transforms manufacturing by enabling robots to understand context, adapt to changes, and make autonomous decisions. The success of agentic systems in manufacturing demonstrates their potential in complex environments where multiple systems must coordinate and adapt to changing conditions. Now let's explore how agentic systems are augmenting human decision-making and solving complex optimization problems. Traditional decision support systems rely on fixed rules and static analysis. LLM-based agents, however, can understand context, reason about trade-offs, and provide adaptive recommendations aligned with business objectives. Modern decision agents analyze multiple data streams, understand complex business contexts, and generate actionable insights. They can explain their reasoning, adapt to changing conditions, and integrate domain expertise with data-driven insights. This makes them invaluable for strategic planning and operational optimization. In the financial sector, J.P. Morgan Chase's LOXM system analyzes market data, news, and social media to identify investment opportunities. In healthcare, HealthPal and DeepPill provide personalized treatment recommendations. In industry, Siemens's MindSphere and ExxonMobil's Energy Outlook optimize manufacturing and resource planning. These examples show the versatility of agentic systems in decision support. Global supply chains are complex, with multiple stakeholders, variable lead times, and frequent disruptions. Traditional tools struggle to balance cost, speed, and sustainability. A multi-agent system can orchestrate end-to-end supply chain optimization, making real-time decisions and adapting to disruptions while balancing competing objectives. The supply chain system uses a strategic planning agent for long-term strategies, an operational optimization agent for day-to-day logistics, a risk management agent for disruptions, and a sustainability optimization agent for environmental goals. These agents collaborate through shared context, real-time data, and continuous scenario planning, ensuring the supply chain remains resilient and efficient. The system interfaces with ERP, TMS, WMS, market intelligence, weather systems, supplier networks, and more. An integration layer manages APIs, real-time data streaming, event processing, and blockchain for traceability. This comprehensive integration enables dynamic, context-aware optimization across the entire supply chain. Traditional supply chain systems operate with limited context and struggle to adapt to rapid changes. Agentic systems enable natural language interaction, real-time adaptation, proactive risk identification, balanced optimization, and integration of human expertise. This leads to more resilient, efficient, and sustainable supply chains. Throughout this video, we've seen how agentic systems powered by LLMs are transforming creative workflows, language processing, robotics, and decision support. These systems represent more than just technological advancement. They mark a fundamental shift in how AI can understand, reason, and participate in complex human endeavors. From film production to supply chain management, agentic systems are becoming valuable partners, not just tools. While we've focused on 4 key domains, agentic systems are finding applications in many other fields, including education, scientific research, healthcare, and environmental protection. Their ability to adapt, learn, and collaborate makes them suitable for a wide range of complex, dynamic environments. The future of AI lies in augmenting human capabilities through intelligent collaboration. The real-world applications we've explored demonstrate that agentic systems are becoming valuable partners, not just tools. They show us that the future of AI is not about replacing humans, but about augmenting our abilities through intelligent collaboration. By combining reasoning, context awareness, and adaptability, these systems are redefining what's possible in automation and decision-making. To recap, agentic systems powered by LLMs are transforming creative industries, language processing, robotics, and decision support. Their ability to maintain context, adapt to feedback, and collaborate with humans sets them apart from traditional AI tools. As these systems continue to evolve, they will unlock new possibilities across countless domains. In the next chapter, we'll review key concepts of agentic systems, explore emerging tools and research, and discuss the challenges and opportunities ahead. As artificial general intelligence and superintelligence become more tangible, understanding the capabilities and limitations of agentic systems will be crucial for harnessing their full potential. Let's clarify a core concept. An agentic system is an AI system that combines LLM-based reasoning with goal-directed behavior and autonomous decision-making. Unlike traditional AI, agentic systems can understand context, plan actions, adapt to feedback, and operate with increasing autonomy, all while maintaining alignment with human intentions. Multi-agent collaboration refers to the way multiple specialized agents work together, each handling a specific aspect of a complex task. By sharing context and feedback, these agents can solve problems that are too complex for a single agent, ensuring alignment across creative, technical, and operational requirements. Thank you for joining this deep dive into the common use cases and applications of agentic systems. As you consider deploying these systems in your own field, remember their unique capabilities and the importance of maintaining alignment with human values and intentions. Stay tuned for our next chapter, where we'll explore emerging tools, research, and the future of AI.